Hello viewers, in the earlier classes we have learnt heteroscedasticity and problem of autocorrelation. Today we are going to learn the problem of multicollinearity. Here there are 4 or 5 pertinent questions. They are: what is multicollinearity? How do we estimate the parameters when there is a problem of multicollinearity and less than perfect multicollinearity? What are the consequences of multicollinearity? How do we detect the problem of multicollinearity? Then how do we overcome the problem of multicollinearity? For all these questions we are supposed to answer in this lesson. First of all, now I would like to take up meaning and nature of multicollinearity. The term multicollinearity denotes the presence of linear relationships among explanatory variables. This term is due to Ragnar Frischs. It connotes the existence of perfect or exact linear relationship among some or all explanatory variables of regression model. For the k variable regression involving explanatory variables like x1, x2 up to xk, where x1 is equal to 1 for all observations to allow for the intercept term, an exact linear relationship is said to exist if the following condition is satisfied. That is, lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 plus and so on so forth plus lambda k xk is equal to 0, where lambda 1, lambda 2, lambda 3 and so on so forth up to lambda k are constants such that not all of them are 0 simultaneously. Today the term multicollinearity is used in a broader sense to include the case of perfect multicollinearity as explained earlier, where x variables are intercorrelated but not perfectly, so as follows: lambda 1 x1 plus lambda 2 x2 plus and so on so forth plus lambda k xk plus vi is equal to 0, where vi is a stochastic error term. Lambda 2 x2, by doing some mathematical manipulation, here lambda 2 x2 is equal to minus lambda 1 x1 minus lambda 3 x3 minus and so on so forth minus lambda k xk. Then this can be written as x2 is equal to minus lambda 1 divided by lambda 2 x1 minus lambda 3 divided by lambda 3 x3 minus and so on so forth minus lambda k divided by lambda 2 xk. This is a case 1. But in the case of 2, lambda 2 x2 is equal to minus lambda 1 x1 minus lambda 3 x3 minus and so on so forth minus lambda k xk minus vi. Then again by doing some mathematical manipulation, this can be written as x2 is equal to minus lambda 1 divided by lambda 2 x1 minus lambda 3 divided by lambda 3 x3 minus and so on so forth minus lambda k divided by lambda 2 xk minus vi by lambda 2. Here we can find the difference between perfect and less than perfect multicollinearity. For instance, lambda 2 is not equal to 0, then the above equation 1 can be written as x2i is equal to minus lambda 1 by lambda 2 x1i minus lambda 3 divided by lambda 2 x3i minus and so on so forth minus lambda k divided by lambda 2 xki, which shows how x2 is exactly linearly related to other variables or how it can be derived from a linear combination of other variables. In this situation, the coefficient of correlation between the variable x2 and the linear combination on the right hand side is bound to be unity. Similarly, if lambda 2 is not equal to 0 as in the case of equation 2, then it can be written as x2i is equal to minus lambda 1 divided by lambda 2 x1i minus lambda 3 divided by lambda 2 x3i minus and so on so forth minus lambda k divided by lambda 2 xki minus vi by lambda 2, which shows that x2i is not an exact linear combination of other x's because it is also determined by the stochastic error term, that is vi. By looking at the case equations pertaining to 1 and 2, we can see the difference between perfect multicollinearity and less than perfect multicollinearity. Case 1 reflects the perfect multicollinearity, whereas case 2 reflects the less than perfect multicollinearity. Then naturally, there is a question, that is, what causes for the problem of multicollinearity? Technically speaking, there are many reasons for the problem of multicollinearity. Among them, two important causes are pertinent to mention here. One is, there is a tendency of economic variables to move together over a time. All these variables, all the economic variables, in the case of growth, they will try to exhibit an upward trend. In the case of recession, they will try to exhibit downward trend. By and large, we can say that growth and trend factors in time series are the most serious cause of multicollinearity. And another important cause for the problem of multicollinearity is lagged values of some explanatory variables as a separate independent factors in the relationship. Naturally, the successive values of a certain variable are intercorrelated. For example, income in the current period is partly determined by its own value in the previous period, and so on. Thus, multicollinearity is almost bound to take place in distributed lag models. If the multicollinearity is perfect, the regression coefficients of the x variables are indeterminate and their standard errors are infinite. If multicollinearity is less than perfect, the regression coefficients, though determinate, poses large standard errors, which means the coefficients cannot be estimated with great accuracy. These are the two important causes for the problem of multicollinearity. The problem of multicollinearity especially can be seen in the case of multiple regression. In the case of simple regression, there is no question of problem of multicollinearity, because the problem of multicollinearity explains about the linear relationships among the explanatory variables like x1, x2, x3. If at all covariance of x1, x2 happens to be 0, there is no question of problem of multicollinearity. If covariance of x1, x2 is not equal to 0, the problem of multicollinearity is likely to take place. Then if at all there is a problem of multicollinearity, how do we estimate the parameters? If there is a problem of multicollinearity in a given data, the coefficients may become indeterminate and the variance value would be infinity. If there is a perfect multicollinearity, the problem is more serious. If multicollinearity is less than perfect or not so perfect, the value of the variances would be large, despite value of the coefficient may not become indeterminate. If at all there is a problem of multicollinearity, what are the consequences that we are supposed to come across? The consequences of the problem of multicollinearity are: number 1, the estimates of the coefficients are indeterminate. If the OLS estimate coefficient may be obtained, their standard errors tend to be large as the degree of collinearity between the variables increases. Because of the large standard errors, the confidence intervals for the relevant population parameters tend to be large. By virtue of 1 and 2, in the case of high multicollinearity, the sample data may be compatible with a diverse set of hypotheses. Hence, the probability of accepting a false hypothesis increases, especially type 2 error. As long as multicollinearity is not perfect, estimation of the regression coefficients is possible, but the estimates and their standard errors become very sensitive to the slightest change in the data. Another consequence is the estimates of the coefficients may be unbiased, even though intercorrelation is strong, may not ensure blue. Blue means best linear unbiased estimators. Many writers seem to accept that even if standard errors are high or large, this may not be so in all cases, since both the numerator and the denominator of the formulae of the variables will usually be affected by terms involving sums of cross products of the x's, so that the final size of variance of the betas may not be large. For instance, I would like to quote L.R. Klein's comments here. To Klein, multicollinearity is harmful when if r square xi xj is greater than or equal to r square y x1 x2 up to xk, where r square xi xj is the simple correlation between any two explanatory variables, that is xi xj, whereas capital R square is the overall or multiple correlation of the relationship. In light of this, we have to detect the problem of multicollinearity. Then here is a question, how do we detect the problem of multicollinearity in a given data? Many writers stated that multicollinearity is a question of degree and not of a kind. The meaningful distinction is not between the presence and the absence of multicollinearity, but between its various degrees, because to them multicollinearity is bound to take place. Either it may be cross section data or it may be time series data. Therefore, there is no need to test for its presence. To some of them, multicollinearity refers to the condition of the explanatory variables that are assumed to be non-stochastic. Essentially, it is a feature of the sample and not of the population. Keeping all these facts in view, we do not test for multicollinearity, but we measure its degree in any particular sample. However, broadly speaking, there are two ways to find out the problem of multicollinearity in a given situation. One is graphic method and the other one is testing methods. In the case of graphic method, we have two important views. One is Ballantyne's view, the other one is Frischs three-dimensional diagram. Now, I would like to dwell upon graphic method, especially on Ballantyne's view. Ballantyne's view can be seen with the help of circles. We have 5 figures, figure A, figure B, C, D, E. In one circle, there is a dependent variable, that is y. In another 2 circles, we have 2 independent variables, x2 and x3. Figure 1 indicates no collinearity between the explanatory variables, because there is no overlapping. But in the case of figure B, figure C, figure D, figure E, we have a problem of multicollinearity, because there is some sort of overlapping between x2 and x3 circles. In the case of figure B, there is a small overlapping, but the overlapping is increased from figure B to figure C and figure C to figure D and figure D to figure E. Therefore, we can say that in figure B there is a low multicollinearity, in figure C there is a moderate multicollinearity, in figure D we can say that there is a high multicollinearity, in figure E there is a very high collinearity. The another important graphic method is Frischs three-dimensional diagram. We have a figure 1 and figure 2. In the case of figure 1, there is no problem of multicollinearity. In the case of figure 2, we have a problem of multicollinearity. In the first diagram, the scatter diagram will take the shape of an egg, and the best fitting line in the 2-dimensional diagram will become the best fitting plane in the 3-dimensional diagram that passes through the egg shaped scattered. In the case, there is no multicollinearity, but if multicollinearity is present in the given data, it will not be a plane through the egg shaped scattered diagram, but it will be different planes cutting each other as shown in the figure 2. Therefore, we may not be able to obtain a best fitting plane for the given data. Thus, we can say that the multicollinearity problem finally resolves into different hypotheses being compatible with the given data. Apart from these 2 graphic methods, there are other testing methods to detect the problem of multicollinearity. First one is Frischs confluence analysis, a modified version. The seriousness of the effect of multicollinearity seems to depend on the degree of intercorrelation, that is R xi xj, and the overall correlation coefficient R y x1 x2 xk. Thus, one might suggest that the standard errors, the partial correlation coefficients and the total R square may be used for testing for multicollinearity. Yet, none of these criteria by itself is a satisfactory indicator of multicollinearity, because large standard errors do not always appear with multicollinearity. Furthermore, large standard errors may arise for various reasons and not only because of the presence of linear relationships among the explanatory variables. The intercorrelations of the explanatory variables need not be high for the value of the betas and their standard errors to be affected badly. That is, R xi xj is not an adequate criterion by itself. The overall R square may be high and yet the results may be highly imprecise and insignificant with wrong signs and or large standard errors. However, a combination of all these criteria may help the detection of multicollinearity. Its essence can be found in a revised version of Frischs confluence analysis. Frischs confluence analysis can also be called as a bunch map analysis because it combines large standard errors with intercorrelations of the explanatory variables and the overall R square. So, therefore, the Frischs confluence analysis can be called as bunch map analysis. How do we conduct the Frischs confluence analysis? Here the procedure is to regress the dependent variable on each one of the explanatory variables separately. Thus, we obtain all the elementary regressions and we examine the results on the basis of a priori and statistical criteria, that is yi is equal to beta naught plus beta 1 x1i, beta 2 x2i plus beta 3 x3i plus beta 4 x4i plus ui. For this, we have to examine the relationship covariance between x1 x2i, x1 x3i, x1 x4i, x2 x3i. We have to examine all these covariances are based on the elementary regression results. Frischs classified a new variable as useful, superfluous or detrimental. If the new variable improves R square without rendering the individual coefficients unacceptable on a priori considerations, the variable is considered useful and retained as an explanatory variable in the model. If the new variable does not improve R square and does not affect to any considerable extent the values of the individual coefficients, is considered as superfluous and rejected. If the new variable affects considerably the signs or the values of the coefficients, it is considered as a detrimental. Apart from this Frischs confluence analysis, there is another important test to detect the problem of multicollinearity, that is the Farrar-Glauber test. This test has been recently developed by Farrar and Glauber to detect the problem of multicollinearity. Actually, Farrar-Glauber test is a set of 3 tests, or it is an amalgam of 3 tests. The first test is chi-square test. The chi-square test is meant to detect the existence and the severity of the multicollinearity in a given function, including several explanatory variables. The second test is an F-test for locating which variables are multicollinear. The third test is a Ttest for finding out the pattern of multicollinearity. Farrar-Glauber consider multicollinearity in a sample as a departure of the observed excess from orthogonality. Farrar-Glauber used 3 tests. One is chi-square test. A chi-square test for the presence and severity of multicollinearity in a function with several explanatory variables. Based on this, the analysis suggests that multicollinearity may be considered as a departure from orthogonality. The stronger the departure from orthogonality, that is, the closer the value of the determinant to 0, the stronger the degree of multicollinearity and vice versa. Starting from this fact, Farrar-Glauber suggested the test for detecting the strength of multicollinearity over the whole set of explanatory variables. The basic hypothesis here is H0, the excess are orthogonal, not multicollinear. H1, the excess are not orthogonal, multicollinear. H0 is a not multicollinear, H1 is a multicollinear. For this, the chi-square principle is minus n minus 1 minus 1 by 6 into 2k plus 5 into log e of value of the standardized determinant, where chi-square star is an observed value, n is the size of the sample, k number of explanatory variables. Chi-square star follows distribution with v is equal to 1 by 2k of k minus 1 degrees of freedom. If the observed chi-square star is greater than the theoretical value of chi-square with 1 by 2 k of k minus 1 degrees of freedom, we reject the null hypothesis, that is the assumption of orthogonality, and we accept that there is a multicollinearity in the function. The higher the observed chi-square star, the more severe the multicollinearity, which is conversely true. Likewise, Farrar-Glauber also used an F-test for the location of multicollinearity. To conduct the F-test, we have to calculate the multiple correlation coefficients for all variables like x square, x1, x2, x3 up to xk and so on and so forth. Then we have to calculate the computed value of f. After calculating the computed value of f, that is f star, we are supposed to compare the calculated value with that of theoretical value f. If at all calculated value is greater than the theoretical value, that is f star is greater than f, we accept that the variable xi is multicollinear, and in a way we reject the h naught. If at all f star is less than f, we accept that the variable xi is not multicollinear. Likewise, Farrar-Glauber also used Ttest for the pattern of multicollinearity. This Ttest aims at the detection of the variables which cause multicollinearity. In order to conduct the Ttest, we have to calculate the partial correlation coefficients among the explanatory variables. For instance, I would like to say one principle: r square x1 x2 x3 is equal to r12 minus r13 r23 whole square divided by 1 minus r square 23 into 1 minus r square 13. Likewise, we have to calculate the partial correlation coefficients in order to conduct the Ttest. After calculating the T with the help of a principle, again we have to compare calculated T value with that of theoretical T value. If at all the calculated T value, that is T star, is greater than the theoretical T value, that is T, we accept that the partial correlation coefficient between the variables xi, xj is insignificant. In a way, we can say that the variables xi, xj are responsible for the multicollinearity in the function, which is conversely true. In the sense, T star is less than T, we accept that xi and xj are not the cause of multicollinearity, since their partial correlation coefficients is not statistically significant. Apart from these methods, there is another method for detecting multicollinearity, is the method of principal components. Then what can be done if multicollinearity is serious? In the case of detection, there are no infallible guides, because multicollinearity is essentially a sample problem. However, the following rules of thumb can be tried, the success depending on the severity of the multicollinearity problem. Some writers have suggested that if multicollinearity does not seriously affect the estimates of the coefficients, one may tolerate its presence in the function, although the efficiency of the estimates is to a certain extent impaired. Others have suggested that exclude some of the factors which cause multicollinearity. So, now we would like to, after detecting the problem of multicollinearity in a given data with the help of the graphic method, Frischs confluence analysis and Farrar-Glauber test, we have to find out the solutions to overcome the problem of multicollinearity. Here, now I would like to dwell upon the remedial measures. Multicollinearity may affect only a part of the betas, while other estimates may remain fairly stable and reliable. In this case, the reliable betas may be used for any purpose, forecast or policy formulation. The above solutions are suggested if the problem is not so serious. If, however, the problem of multicollinearity is serious, one should adopt one of the following corrective solutions. They are the method of restricted least squares. Second one is the method of pooling cross-section and time series data. Third one is Durbin's version of generalized least squares. Fourth one, the method of mixed estimation technique of Thiala and Goldberger. Fifth one is increase the sample size. Next, substitution of the lagged variables for other explanatory variables in the distributed lag models. And another one is introduction of additional equations in the model. And another remedial measure is application of the principal components method. Another remedial measure is transformation of variables. So far, we have learned the problem of multicollinearity. We have learned the meaning and nature of multicollinearity. The problem of multicollinearity will crop up if at all the assumption covariance of xi xj is equal to 0 is violated. If at all there is a problem of multicollinearity, the consequences are very serious. If at all there is a problem, variance of the estimates are very large. Sometimes if at all there is a perfect multicollinearity, estimates are indeterminate and the standard errors are infinity. Then we can detect the, if at all there is a problem of multicollinearity in a given situation, we have to detect its presence. In order to detect, we have to apply the graphic method and testing methods. In graphic methods, we have two views. One is Ballantyne's view, the other one is Frischs three-dimensional diagram. In the case of testing methods, we have two important tests. One is Frisch confluence analysis, which can be called as bunch map analysis. The another test is Farrar-Glauber test, which is an amalgam of three tests. One is chi-square test, the other one is F-test, the other one is T-test. After detecting the problem of multicollinearity, we have to find out some solution to overcome the problem of multicollinearity. If the problem of multicollinearity is not so serious, we should not bother about it. If at all the problem of multicollinearity is severe, if at all it is serious, then we have to apply some remedial measures or solutions to overcome the problem, like method of restricted least squares, the method of pooling time series and cross section data, transformation of variables, increase the sample size, mixed estimation technique that had been suggested by Thiel and Goldberger, and so on and so forth.